How this controls will. Okay, good evening. So for the crowd on the internet who will be watching the streaming or the YouTube version of this, I will briefly introduce myself and the topic of tonight's presentation. My name is Aleksander Molak, and the topic for tonight is causal discovery in Python. So this talk has a practical aspect, but it also has a theoretical aspect, and this is because the topic of causality in general requires certain assumptions, and I'm deeply convinced that understanding certain assumptions and certain theoretical concepts will make it easier for you to work smoothly with those ideas and tools that we'll discuss today. Okay, without further ado, let's go. Let's start with an agenda. So we'll start with a quick introduction. Then we'll talk about causal inference and causal discovery. So these are two slightly different sub areas of causal research, of causal learning. Then we'll talk about causal graphs. Then we'll talk about methods of causal discovery. So we are focusing on causal discovery in particular today. But as we have a little bit more time, and you will be, if you will be interested in hearing more about causal inference as well, I think we can also talk about it. And finally, we'll do a little bit of a couple of practical examples in Python using certain libraries. So I will share with you like very basic workflow for causal discovery, and also hopefully we'll be able to see in action how certain concepts that we'll discuss before can be leveraged, and how they can help in interpreting the results of a causal discovery process. And finally, we'll have Q&A. But as we agreed before, please feel free to just interrupt, unmute yourself, and ask questions as we go, because I believe that's something that might give you just more value from this talk. And you can prepare your QR code reader if you have one, because we'll have a couple of interactive materials along the way. So this might be helpful for you. Kaiti, I have to ask you one question. Do you see this control panel here or not?
Control panel for
Zoom?
Yes.
Okay, I will try to remove it somehow, but I don't know how. So I will leave it because I don't know how to remove it.
Is it affecting your presentation? Is it okay, or?
No, for me it's fine. I was just thinking that it might cover something along the way, but let's check it. Maybe it will be fine. Okay. Okay, great. So let's go. Let's do the introduction. Then. So here are two main resources for today. The repository is on your left, and on your right, it's a direct link to the notebook that is within this repository, inside this repository that the left QR code links you to. And also for those of you who do not have a QR code reader, you can use this address. So you github.com, Aleksander Molak talks and workshops, and then you should find it as PyData Hamburg. I will leave the screen on for a couple of seconds, so you can copy the address. Okay. So let me introduce myself, like in like 3 or 4 sentences. I'm a machine learning engineer and researcher at Iron Scales, and machine learning researcher at TensorCell. My main areas of expertise or focus are natural language processing, probabilistic modeling, and causal inference, or causality in a broader sense. I also write a thing that is called Sunday AI Papers, which is a weekly microblog on LinkedIn. So if you're interested in the bleeding edge, most recent papers in the areas of NLP, probabilistic machine learning, causal machine learning, and so on, feel free to connect on LinkedIn. I'm trying to write Sunday AI papers weekly, but lately it was a little bit challenging, so it was bi-weekly. But this is something between weekly and bi-weekly anyway. I'm also interested in complex systems, psychology and neuroscience, and psychology and neuroscience are parts of my academic background. And I really enjoy traveling with my wife, running. I love vegan food, and I really like languages, natural and programming. Okay, so let's talk about causality. What is causality? So now I will ask a question. That's my question to you. So what are intuitions? What is causality in general? So we are not looking for like a precise definition here. It's more like about your understanding. It's always very interesting to hear how people have different ideas sometimes about this. So what is causality? What are your ideas about causality?
So there are two main categories of causality in my mind. One is the constructor sequence of fundamental physics. And then another is the correlation between preceding and succeeding events.
You say there are you have two ideas or two concepts of causality in your head. And the first one is about physics and about physical world. So how one thing, like what causes the other thing, is that correct?
Well, both. The concept in general is one of succession of events in which one event precedes another. How you characterize the events will determine the meaning of that connection. But you know, I have two intuitions. One is that there are fundamental events in the physical world which are have a so there's one state follows another state predictably. Characteristics of the state, prior state, determine characteristics of the subsequent state. Those may be stochastic, but that's the fundamental, underlying substrate, the material substrate. But when we talk about observations at the macro scale, that's a bit different because we don't have a complete description of the microstate, reductionistic description. We only have correlations between sets of properties in a prior state and sets of properties in a subsequent state.
Great. I think these are great intuitions, Anthony. Thank you so much for sharing this. I think you touched upon a couple of very interesting and crucial things. And well, what you said about physics and reductionistic explanations of large-scale phenomena is something that I think is even much more deeper than we will be able to touch today. But nevertheless, I think many of those intuitions that you mentioned will come back in today's talk. So thank you so much for sharing. Do we have any more voices, any more intuitions?
Maybe in a perspective or history of science, that there were once a belief that if you know the state and the movement of every particle in the universe, you can predict the future, like this old school determinism in a way. And this has proven wrong. So, but this was a working hypothesis of modern science, a really a really long time, and there are new concepts and new. I come from the social science, political science, and we know agent and system interactions where you have a practice, and part of the practice is a reflexive part. So everything is shaped by circumstances, but you can shape the circumstances. So the whole concept of causality isn't gone, but is much more narrow in a way, and moved away from this classical determinism in a way. So
Thank you. That's a very interesting perspective. So as I understand, a perspective that you gave us is more of a complex systems perspective, where we don't have a deterministic system where high level emergent properties might have, let's say, a chaotic relationship with a lower level, simpler processes. That's very interesting. And this is something that I think those intuitions that we got from Anthony and from Dennis, they give us like a very broad perspective on what causality can be. That it can be many different things. So what we'll try to do today, we'll try to find a framework that is actionable, that in a sense is abstracting away a lot of those very important and very, very deep ideas that we can meet when we think deeper about causality. Okay, so let's see what Wikipedia says. Now, after everything you said, this seems I think this might seem very simplistic, but this is the definition from Wikipedia, a definition of causality as understood in physics, and it says causality is the relationship between causes and effects. Is it a good definition? Well, I don't know. It seems that it's potentially a circular definition because we try to explain causality using causes. But whatever, this is what it is. But this is just one example of many, many definitions of causality that are out there. And in another talk, I have a couple of examples of those. Here, I only have this one. But as I said before, we'll try to find a framework that lets us abstract a lot of very difficult, philosophically difficult things, and give us a tool that is very actionable, that we'll be able to build upon or build with using this tool. This definition comes from Judy Appel, who you could think of as a godfather of causality. So he devoted most of his career to research on causality, first on Bayesian networks, then actually building a causal framework with his students as well. And his definition is very, very simple. So it says A is a cause of B if B listens to A. And this listens to, well, sounds, well, metaphorically, of course, but what it means is that if we change, so if we make an intervention on A, then B will also change. And as Anthony mentioned before, it will change in a predictable way, given certain circumstances. So this is the definition that we will basically use implicitly today. So most of the stuff that we will work with will somehow depend on this definition. But well, you could argue that some methods might be less requiring of this definition than others. Anyway, do you have any comments or questions at this stage? Okay, so I'll take it as a no. Okay, so now I have another question to you. Why model causality? So we have machine learning, we have statistical learning, we have deep learning, and all this fancy, very complex models today, like transformer models that can model like very, very, very complex functions in high dimensions. And this has been, these models has been proven actually very effective as well, right? So today we are able to solve many problems that even 10 years ago, it would be hard to imagine that we could solve those problems using computers in like a relatively easy and efficient way. So why should we model causality? Why should we even bother if machine learning is so good? Do you have any intuitions from this?
I would say to reduce future uncertainty.
Mm-hmm. To reduce future uncertainty. So you would see a difference between the way that we can try reducing future uncertainty using regular machine learning versus causal models?
Again, the questions?
So you said that reduction of future uncertainty is something that could motivate us to use causal models. So my question to you is, if you see, and if yes, what is the difference between regular machine learning, as complex as you wish, and causal models in this regard, in the context of future uncertainty that you mentioned?
Mm-hmm. I really don't know. I'm really into the answers provided by this talk. So yeah, but I think to one have to reduce future uncertainty to increase the rationality of one's action. So this would be the purpose in the first place. So
great. Okay, great.
To design interventions, perhaps?
To design interventions. What would that mean, to design interventions?
To exploit the discovered causal structure in order to effect some control outcome. And, you know, a simple example, like treating a disease with a specific molecule.
Excuse me, we also have a raised hand from Dietrich.
From Maciej.
Yes, hello, Maciej, yes. So I would also say that to debug wrong causality. So, for example, there were recent examples of chest X-rays of the patients with COVID-19. That the machine learning algorithm was very good at detecting whether the patient will have some severe COVID case. It will be a severe COVID case. But what it appeared that the machine learning model just learned to differ from the stand-up X-ray chest from the laying down X-ray chest. And if someone had laying down X-ray chest, they already had some problems. So I would say that if we discover what's the causality discovered by the machine learning model, we can then discover how useful this model is.
So, okay, great. Thank you for sharing. Thank you, Anthony, and thank you, Maciej. Great intuition. So, Maciej, you mentioned something that we call in causality a confounder. A confounder is a variable that is affecting both our predictor and the variable that we are trying to predict. Okay, and this is something that can have a very, very profound effect on the way we compute our results, we interpret our results. We also have another answer here in the chat from Tara. And this answer says for interpretability. So this, I feel that this goes maybe a little bit into the direction of what you mentioned, Anthony. You said about interventions. So this is slightly different, but I feel there is a common, let's say, common root to those two answers, actually to all the three answers that we got. Okay, great. So
we also have
now,
we also have one input from Tara. She said it would be for interpretability.
Interpretability. Yeah. So this is what I just mentioned from Tara. Yeah, exactly. Thank you. Great. So so now let's go and let's see another angle why we could be interested in modeling causality. So let's start with another question: how to increase the number of non-commercial space launches per year? And I will give you an answer. To increase the number to do this, we should increase the number of PhDs in sociology in the US. Do you think it's a good answer? Okay. Oh, we have another answer here from James: to free humanity from correlation-based thinking. That's a very nice answer. Thank you. Somebody unmuted themselves to say something, I guess. So please feel free.
Yeah, Aleksander, that's great. Sorry. I guess I will go ahead. I just regarding your question is whether it's clear the answer about increasing the number of PhDs. I guess you found probably the very root of the problem in your assumptions that you made. Maybe you can depict them as a graph, but and then you introduce that as an answer. But I guess this is my answer because I'm also coming from the field of machine learning. Probably it's not very clear, but that's what I understood. It's not very clear how you derived this conclusion, but I'm pretty sure that you derived that based on some assumptions and associations that you made along the way between different variables. Mm-hmm.
Yeah, so actually this comes from the real world data, and this answer is 100% data driven. And as you can see, those two variables are very, very highly correlated. I'll show you also another view on this data, which is a scatter plot. And you can see that this correlation is really, really strong. And now, if we use a regular machine learning algorithm, like in this case, this is a linear regression line fitted here, as you can see. This answer would be a very, very good answer in terms of many metrics and many popular metrics that we use for assessing the quality of our models. And of course, this idea, when we think about it as humans, and we talk about PhDs in sociology as a cause for space launches, we might think, hey, actually, how could that work, right? And we can start asking questions about the causal mechanism, but classical machine learning algorithms cannot do this because what they do, they actually focus on correlation, and that's actually the hard part. But let's think, how could we address this? So I will start with causal inference, although the main topic of our today's talk is causal discovery. I will start with causal inference because, in a sense, I think it's a better start. So what is causal inference? Well, causal inference is a process of estimating causal effects from observational data. So Anthony mentioned before that we can try using causality for designing interventions, but what we're actually trying to do in this, at least in this view that I'm presenting now, we are trying to understand, to read the interventions from the data. So it would be the opposite direction in a sense. And now, to do this, we need a causal structure. So as we said a minute ago, traditional machine learning or statistical learning algorithms cannot find out causal relationships because they do not have a causal model of the world, at least most of the models that we are using today. Now, so we need some causal structure to provide these algorithms with. And you can think of it as adding a story to the data. So causal structure is something like in our example, right? We say, hey, is it possible that doctorates in sociology cause or influence the number of non-commercial space launches, like causally influence in the same year? You know, if we look at this and see that it happens the same year, it's not like we have more sociologists in the society, and maybe in some way it inspires other people or inspires the policy change that's, you know, that influences the number of space launches. It happens in the same year. So we would be very, I guess so, most people would be very suspicious about this and would say, you know, maybe there's something else that actually influences both things, right? Maybe it's like financial situation in certain institutions or something, right? We would probably go and try to find something. And the something is a story. It's the type of narrative that we find plausible given causal models of the reality that we've learned during the course of our own lives. So those models also need these types of narratives, these types of stories. And and this is all about causal inference. So if we have data and we have a story about data, so about this, you can think about the story also as a some description of the data generating process. Then those models are able, under certain assumptions, to find and estimate true causal effects in your data that will not be susceptible to misestimates that would appear there if we only rely on correlations. And I see that Giant wrote in the chat that correlation does not imply causation. Exactly. So this is exactly an example of this. Now let's talk about causal discovery. We can go back to this data and story later if you want. So causal discovery is a process of estimating causal structure from observational data. So now, first we said, okay, to perform causal inference, we need something extra. Not only our data set, we also need the story or some information about data generating process. And now we are saying that there's another process called causal discovery that leads us to discover the story or read the story from the data. So it's like reading the story from the data and observational data. We can view this also from a slightly different perspective, going back to this starting from regular machine learning. We could say that, excuse me, we could say that in machine learning, regular machine learning, we have data and then we have a model, and this model is trying to leverage the relationships between variables in our data sets. But there's also certain data generating process that generates this data. But our machine learning model is completely naive when it comes to this data generating process. So if there are confounders in the data generating process, our machine learning model will not know about this. So it will not know that there is a confounder in our data set. And also a little detour here that I think some of you who are machine learning practitioners might find interesting is that when we are training machine learning models, we often think about regularization techniques as something that might improve our model's quality. And that's certainly true in many various meanings, because we can reduce overfitting and so on and so on. But from causal point of view, regularization might be actually very detrimental. So if we have a highly regularized tree-based method, like maybe random forest or maybe gradient boosting, and we train these models, and they will push. Even let's take a regression with regularization. You will notice that variables that are less relevant their coefficients will be pushed towards 0, and this makes the model, in a sense, in many scenarios, more robust to overfitting. But at the same time, what we are doing, we might actually favor variables that are confounders and mute the true predictors, because those confounders might have relationships to a couple of predictors. And in this sense, they will have a higher predictive power than any of those predictors individually. But this predictive power might be at the same time very dangerous, in a sense that that the model leveraging those confounding variables will be even further from the true causal relationship, the true causal structure between our variables. So in case of any concept drift, that might be very, very detrimental. So this is something that might be counterintuitive, that regularization might have this dark side, let's say. But this is what it is. So when I understood this for the first time, I was very surprised, and I thought, wow, that's really interesting. And in a sense, it's something that can also be very actionable if you care about causal relationships when modeling your problems. Okay, so let's go back to the graph. We said that in machine learning, our model is naive in terms of data generating process, and it only relies on the data. Now, in causal inference, we are taking some information about the data generating process, and we also send it to the model. We provide our model with some information about this. And in causal discovery, we are again getting this structure, but we are trying to estimate it from the data itself. Okay? So this leads us to a situation where we actually have another estimating building block here. So it's like, it's another type of a model that is trying, that we are trying to fit to the data, but we are trying to fit it to the data using pretty different logic than in case of our regular machine learning model. And now, as you see, all those models here, this is all very, very similar if we don't look here, right? And this is not an accident, because when we are estimating causal effects, we actually can use pretty much the same models. Maybe not always, and we are not always using them, but in many cases we can just use the same set of models that we are using for regular machine learning. The only modification is that we need to provide them with this causal structure, the information about causal structure. And causal discovery, so this little block is the main focus of our talk today. Okay, so now it's time to talk about causal graphs, but before we go there, I will ask you if we have any question regarding what we said so far. Does it make sense what we said so far? Do you feel like it clicks for you? Or is there anything that you feel we should talk about a little bit more?
It's pretty clear to me.
Mm-hmm. Good. So as there are no other voices, let's continue to causal graphs. To introduce those causal graphs, we'll talk about an example, and this example will be a fire alarm system. I've seen in the chat that somebody mentioned the book of Why at some point, and if I remember correctly, this example is actually taken from this book, or maybe there was like a very similar example there. Okay, a couple of important assumptions. Our fire alarm system reacts to smoke. So it does not react to fire itself. It does not react to temperature. It just reacts to smoke particles in the air. And we have only 3 elements in this world. In our example, it's fire, which is binary, either there is or no. There is fire or there's no fire. Or the second entity in our world is smoke, which is also binary, yes, no. And there's alarm, also binary, yes, no. Okay. So now, assuming that all those assumptions that we discussed before are true, we can draw a causal graph of our alarm system, and it would look like this. So we have some fire, fire causes smoke, and smoke causes alarm. Of course, in the real world, there might be smoke coming from outside the window, and this is all stochastic and it's not perfect. But for the sake of this example, let's just think about this very simple world when we have fire, smoke, and alarm. Okay, so this is, I guess this is pretty intuitive and doesn't require too much talking. So now let's do something. Let's make it a little bit more abstract. So let's replace fire and smoke and alarm with A, B, and C. But before we do it, I will go back to here and tell you one thing. So one important thing here is that when we have smoke, but we don't have fire, the alarm will ring as well. Okay. If it's a stochastic system, it will ring with some probability. If it's a deterministic system, it will just ring. So this is important because it shows us that in this type of structure, when we control or intervene on the variable in the middle, then the state of the variable here in the beginning is not important, which means in statistical terms, but also in graphical terms, that given smoke, alarm is independent of fire. And this will be true both in deterministic and stochastic scenarios. Okay, so now let's get more abstract. So now we have A, B, and C. And this structure is called, it has its own name. It's called chain. So in a chain, this important feature of a chain is what we discussed before, that given B, C and A are independent. But this is not the only possible structure. And we are only limiting ourselves to the 3 element structures. Another possible structure for 3 elements will be something that we would call a fork. So as you can see, there's a slight difference because now this arrow is not going from A to B, but rather from B to A. Which means in causal terms, if we agree that this graph represents some kind of a causal model, that B is a common cause of A and C. An important feature of the fork is the same as a feature of a chain, that given B, A and C are independent. Okay, but when we don't control for B, they will be dependent, which is also true for a chain. So now what we are talking about, we are talking about graph independence structure, which is closely related to another term, another concept of D-separation. Okay, now let's go to a third example. This is the third structure, and it's called a collider. And collider is very, very special because collider property is precisely the reverse of the properties, or the important properties of a fork and a chain that we discussed before. So A and C will be independent when we are not controlling for B, but when we control for B, they will become dependent. Okay, this might be counterintuitive, but this is true. And now we'll see that it's not only a graphical property, but it's also a statistical property. So I run a simple experiment that I want to share with you now. So what we have here, we have those three variables, A, B, and C is the dependent variable. So we are trying to predict C with both A and B here in all three cases. And we are running a simple linear regression over a simple random data set. So now let's look at the coefficients. Okay, so we have a chain. So chain is a structure that we started with where A causes B and B causes C. And as you can see, we are controlling for B, and B is a significant predictor of C, but A is not. But if we would remove B from here, A would become significant. Same is true for the fork. You can see that we are controlling for B, and A is not a significant predictor of C. But if we would remove B, it will become significant. And you can run this experiment yourself. I will show you a QR code for this notebook in a second. But the situation for collider is different. As you can see, we are controlling for B, and A is a significant predictor of C. So this is very interesting, and this gives us a very powerful tool to learn about dependence and independence between variables in real world data, right? So for every three variables, we can order them in different ways and direct and redirect edges between them and learn something about the independence between those variables. And this is something very, very important, very, very powerful, and very, very basic for both causal inference and causal discovery. Do you have any questions regarding this section? Okay, I'll take it as a no. So now let's talk about causal discovery methods. So we talked about three basic structures, graph structures: a chain, a collider, and a fork. And now we'll talk about three different groups of methods for causal discovery. And some of those methods will actually use those independent structures that we discussed a minute ago. Okay, so there are three families of causal discovery methods. It's not a complete typology, let's say, because you can also have mixed methods and so on and so on. But for the sake of this presentation and general understanding of this topic, I think it's very convenient to think about it this way. So first we have constraint-based methods. And constraint means that we are actually using those graph dependencies that we discussed before. This is also based on a set of assumptions that we will talk about a little bit more in a second. Then we have score-based methods. So score-based methods, they are trying to generate causal graphs and compare them in terms of their fit to the data. And finally, we have functional methods. So functional methods are trying to find functions, are trying to, I'm sorry. So functional methods are assuming that there are functional relationships between variables, and they are trying to leverage asymmetries between distributions like noise distributions and so on. One very important thing is that when we talk about causal structure, or the story that we also the story or the narrative that we provide the model, the causal model, a causal model with, the story is most of the time represented as some kind of a graph. Of course, those graphs might have much more elements than this A, B, and C, but those graphs, if they have at least 3 elements, can be analyzed using those independencies that we talked about before. Okay, so constraint-based methods. As we said, they are leveraging the graph independent structure. They are based on an assumption that there is a mapping between graph independence and statistical independence in the data. Okay, and this assumption is called faithfulness. One example of constraint-based methods is so-called PC algorithm. This is a classic algorithm, classic causal discovery algorithm. And we'll see an example of this algorithm today, and also we'll discuss how it works. So you will see how we can analyze a graph using those d-separations, using the d-separation or like graphical independencies, and how we can find out the causal structure from the data itself, retrieve the causal structure from the data itself. Second family of methods are score-based methods. As we said, those methods are trying to build graphs and compare them in terms of the fit to the data. Now, you can generate many graphs, but in problems with many variables, this is NP hard. So not really practical. So we are using some types of heuristics, some of them pretty smart, to do a search over the graph space in a way that is feasible and is efficient. And one of the examples of score-based methods is greedy equivalence search. So as you can see, this greedy, if you have an intuition that greedy might have to do something with the fact that this problem is NP hard, this is a very good intuition. And finally, we have those functional methods. So they are leveraging asymmetries and irregularities in variables and noise distributions. They assume that the causal relationships might be expressed as functions. So here we have our child, X are parents. So parents in this sense, in this terminology, are variables that are causing Y. So X is causing Y. And we also have some noise. And we have many different types of models with additive noise, non-additive noise, and so on and so on. And one example of functional methods is LinGAM algorithm, which stands for linear non-Gaussian, linear non-Gaussian model. Okay, and as we mentioned before, there are also other methods. Some of them are hybrid, trying to combine score-based methods and independence-based methods. We have methods leveraging reinforcement learning in many different forms. And finally, we have end-to-end causal discovery and inference methods, where we are trying to, in an end-to-end process, we are trying to discover the causal structure and estimate the causal effects. And some of those methods are based, or maybe even most of those methods are based on generative models, which means that they are actually building a generative model that can also not only estimate causal effects, but it can also impute missing data in your files. So this might be pretty convenient, but this is a very some of those methods are really super fresh. So it's like some of them were published like maybe 2 months ago. So this is an ongoing research process. Okay, so now it's time to go and do some practice. Do you have any questions or comments on the previous section before we jump into coding?
Maybe one question, and maybe you mentioned it. Would you say that a random forest model that works with GIN, so to what reduces the most entropy, is a part of one of those families, or would you don't sort this random forest in this context?
So random forest might be used for causal inference. I'm not aware of any paper or any research using using random forest for causal discovery, but it can certainly be used for causal inference. But then it needs to be used in a certain specific way. So random forest just taken like, out of the box won't give you reliable causal estimates. Of course, in certain simple problems it will, because in certain simple problems correlation will be causation actually. But in general, I'm sorry, it won't be true. Does it answer your question?
Yeah, absolutely. Super.
Yes. Great.
Very interesting.
Mm-hmm. Thank you. That was a very good question. Any more questions? Okay. So let's jump to the notebook now. I think we already have links in the chat, thanks to Maciej. Thank you, Maciej. And also we have a collab even, I see. That's great. That's very, very nice of you. Okay, so let's do it. Oh, I see. It has opened in the other, in another window. So, okay. Okay, great. So for today's session, we will use a couple of packages, and let me introduce you to these packages. The most important one is called gcastle. It's called gcastle, but we import it as Castle. It comes from Huawei research team, which is called Noah's Ark. It's a very interesting package. So it's not super popular, but in my opinion, it's the most complete one. So they have implementations of like really cool, really modern methods, also classical methods. One method that we mentioned, which is called GES, which is a score-based method, is not implemented in this package, and that's why we are importing it separately. But I talked to the development team of gcastle, and they are actually working on their implementation of GES, so it will be included in Castle soon. Otherwise than gcastle, we are using networks, mainly for working with graphs, mainly for visualization purposes. We are using NumPy for something, warnings, because gcastle might send you a lot of warnings at this stage in the current version. And what else? And Matplotlib for visualizing stuff. And that's pretty much everything important. Okay, so let's import this. We'll turn off all the warnings, but of course you should not do this in the real life projects. If you want to install the environment, you can do it with the provided YAML file. It's in the repository. Okay, this is some helper function that will build a graph for us. And now let's talk about PC algorithm. So as you might remember, PC algorithm is an example of constraint-based methods. And it is fully based on independent structures in the data. So we will take this example, which comes from a great review paper by Gilmour and colleagues, and we'll implement it then. But first, before we start implementing, let's understand what is going on here. So let's read the description first. PC algorithm starts with a fully connected graph. So it takes all your variables that you have in your data set and builds a fully connected graph of those variables. And then it performs a series of steps to remove edges, okay? So you might, if you think about it, and if you remember the description that we had, the discussion that we had regarding those independencies, you might have an idea where we're going now. And of course, it will happen based on this graph independent structure. And finally, it tries to orient as many edges as possible. And this is not by accident. The formulation is not by accident here. It tries to orient them as many as possible, which means that it won't be able, sometimes in certain cases, it won't be able to direct all edges, right? So in certain cases, we will get something that is called the Markov equivalence class. Markov equivalence class are graphs that have the same sets of independencies. So sometimes, if you remember chain and fork, they will have different directions of edges, of one of the edges, but actually independent structures are identical in both, which means that PC algorithm, as the only thing it can do, it can leverage those independencies, independent structures. It won't be able to decide regarding one or two edges which direction they should be looking at. Okay, so let's say that this is our graph. So we have X and Y causing Z and Z causing W. We said that PC algorithm is starting with a fully connected graph. So this little figure B is showing a fully directed graph between all those variables. And then it removes edges based on the independent structure. So it starts with something very simple. It looks at pairs of variables and sees if there are pairs of variables that are pairwise independent, right? And it tries to find those pairwise independent variables and remove edges between them. Then after this, it is trying to orient the edges between variables that are left. And as you can see this structure here, X, Y, and Z, this is a collider. So the model just took X and Y and controlled for Z and noticed that the variables became dependent when Z was controlled for. So it knew how to orient those edges. Now, between Y, W, and Z, you don't have a collider. We already know that Y is directing here. So the edge from Z to that, we need to have an edge from Z to W, because otherwise, if we had an edge from W to Z, that would create a collider here. And we know from the independent structure that there is no collider here. Oh, thank you, Dennis. Hopefully you'll be able to see the recording. Also, Katie, if it's too long, just let me know, okay? I'm ready to speed up for anybody.
Sure, yes.
Okay. Sorry, again, I was not able to hear you.
Yeah, no problem. Yeah.
Okay, so now let's try to implement it. So we'll take 1,000 samples from a random normal normal distribution, from standard normal distribution for X and 1,000 for Y. So these are our variables that they have no parents, right? And then we'll create Z by simply adding X and Y and adding some Gaussian noise. And then we'll compute W as 0.7 of Z plus again some Gaussian noise. Okay, then we'll create a little data frame out of this, do a sanity check. Now let's do some causal discovery. How we do it? Well, we just take this algorithm, we just take this class PC, we initialize an object of this class. We first imported this from Causal algorithms. And then we just say pc.learn. So we use learn method and we pass our data set with variables. And what we get when we fit the model, it gives us a causal matrix. So this is how it looks. Is it correct? I don't know. Let's visualize this. And we have, okay, X is causing Z. I think this was correct, right? We had X and Y causing Z, and Y is causing Z as well, and Z is causing W, which is also correct. Well, so that's great. Now, this is a very simple algorithm, but as you can see, it's pretty powerful. But is it always powerful? Well, let's see. So let's do some more causal discovery. We'll now generate much more complex data set, actually a set of data sets. But before we go there, let's see if we have any questions or comments. Maybe you have a comment you want to share with us. That would be that's also very welcome. Okay, is it clear so far? Is there anything that you feel we should devote more attention to?
I think everybody is following quite well.
All clear. Thank you.
Great.
Great, Katie. Thank you, Konstantina. Okay, so then let's build some more complex data sets. We'll use to generate them. We'll actually generate random data sets, right? To generate them, we use something that is called a scale-free model. So if you're interested in graphs, you probably heard about this. If not, this is a certain distribution over graph, distribution of edges over nodes that is trying to mimic certain real-world graphs, real-world structures that could be represented as graphs. So scale-free networks is something that was described by Barabasi and Albert. It was a very famous. It was a very famous pair of scientists, both originally from Hungary, and Albert is considered to be actually a godfather of network science, so something that we extensively use today in networking, in security, in many other areas. Great, so we will generate a scale-free network. Now this network will only give us like an empty, let's say, skeleton of a graph without any variables and relationships between them. And then we'll fill in the scale-free graph using 3 different types of relationships and distributions. So first we'll build a linear and Gaussian data set, then linear and exponential, and then nonlinear quadratic data set. This loop will construct this for us. As you can see, this is very fast. We only have 2,000. We have only 10 nodes, 15 edges, and 2,000 examples or observations. You can see our data sets. We store them in a dictionary. Thank you. Okay, got it. Okay, so let's look at those visualizations just to understand what we have there. So we have the Gaussian is Gaussian, looks Gaussian, the exponential looks exponential, and you can see that the nonlinear data set is not linear, right? Those scatter plots are a little bit extended in the horizontal direction, but you should be able to see this still more or less. So that this one is nonlinear, and also the distribution, as you can see, is very skewed. Okay, so we can now visualize the graph that we constructed. So this is our graph based on the scale-free scale-free architecture. This is the same graph, but represented as a matrix. So this is something that we'll extensively use during the presentation. And now we'll do something, we'll compare a couple of methods. So we'll take the PC algorithm that we've seen in the beginning of the notebook, and it performed very, very well for the simple graph that we started with. Then we'll use GES algorithm, which is a score-based algorithm. And then we'll use a LinGAM, which is a functional algorithm, linear non-Gaussian additive model. LinGAM stands for this. And we'll use a certain flavor of this algorithm based on ICA. ICA is independent component analysis. And finally, we'll use Golem. So Golem is a little bit more advanced algorithm. It's it's trying to find a graph using certain methods. I don't want to go too deep into this, but you can just think about Golem as an algorithm that is in a way capable of modeling more complex relationships in your data. And now what we're going to do is that we will run this. I actually ran this before because it takes a little bit of time. So we can look at the examples. It will take a couple of minutes, so I don't want to rerun this. I don't want to lose your time, waste your time. Okay, so the first data set was linear and Gaussian. So this is something that PC algorithm usually works good with. And as you can see, it worked pretty well, but it did not work as perfect as in the first example that we had. So you can see that we have some edges here that are not in the original data. We have some edges that are missing. So on the left, it's the estimated graph, and on the right, it's the true graph. It's a true graph. It's our true graph. So you can see a couple of statistics here. Number of undirected edges is 1. So if you remember, we said that this algorithm might provide us with something that is called a Markov equivalence class. So a graph that is not fully directed, might be partially directed. You can also see that precision in F1 score in terms of finding the edges is not perfect, and false discovery rate is 0.2. So false discovery rate in PC algorithm might mean that we actually have found some undirected edges in our graph, because from the matrix point of view, an undirected edge will be represented as 2 edges, from X to Y and from Y to X, or from like node 0 to, I don't know what it is, 3, and from node 3 to 0, we don't have it. But there are edges like this here. Okay, now GES algorithm. So this is a score-based algorithm, and we said that it's building a series of graphs and trying to fit them to the data and compare them on some kind of fit metric, in terms of some kind of a fit metric like BIC or AIC or other metrics. And as you can see, GES is not doing a very good job here. So it also has 1 undirected edge. This algorithm also might find edges that are undirected, but F1 score is much lower. False discovery rate is much higher than in case of PC. Finally, we have LinGAM, which stands, again, I will say this again because it's important to interpret the results. It's linear non-Gaussian additive model. And because this data is linear and Gaussian, we actually would not expect this model to perform very well. And this is true. It didn't perform like tragically bad, but it's not a very good performance neither. And finally, we have Golem. And as you can see, Golem modeled the data perfectly. So you can see that recall, precision, and F1 score are all 1, false discovery rate is 0, and number of undirected edges is also 0. Okay, the second data set is linear but exponential. So I didn't tell you, but PC algorithm usually works the best on simple Gaussian linear data sets. And you can see this here as well. So you can see that we have like 2 undirected edges already comparing to one in case of the first data set, which was linear and Gaussian. And F1 score is actually slightly better, but precision is worse and recall is better. GES is not performing very well again. Lingam, though, is performing perfectly. So because this data set is non-Gaussian, it's exponential, Lingam is doing, well, a very good job here. And finally, Golem, and you can see that Golem again is doing a very good job here with a perfect fit, similarly to what we got from Lingam. And finally, we have the most challenging data set, nonlinear quadratic. As you can see, PC is not performing very well. It's actually performing pretty poor. F1 score of 0.38, so this is pretty poor. GES is performing a little bit better, but just a little bit. Oh no, actually it's performing the same. That's interesting. Yeah, but it seems that it's actually performing exactly the same in terms of those metrics that we're using. Lingam, well, it's performing very poorly as well. It's even worse than the other ones because the small works well for Gaussian stuff. So we don't have Gaussian stuff here. It's non-Gaussian. And finally, we have Golem, the most complex model in a sense, and it performs, well, it performs not very good, but much better, or relatively better than the other ones. Now, one thing to mention about Golem here is that we only run it for 25,000 iterations, and we could have done this for longer. And there's a chance that this model would give us much better results. So you can run it for 100,000 iterations, even more, and it can get better. Sometimes the likelihood is not dropping here. Maybe H is just moving a little bit, but it's worth trying. So it's worth to experiment. But actually, we haven't run this example now live because of Golem, because of the computational cost that Golem I'm sorry. Yeah, the computational cost that this model is generating. So it would take, the most of those computations would be taken by this algorithm. So it's more complex, it works better on certain data sets, but it also takes much longer to train. Okay, great. So this is the end of the notebook. And I'm just wondering if my presentation is still in the presentation mode after this attack. Yeah, but it seems it is. So this is time for questions. And also this is time if you don't have questions or maybe you don't want to ask your questions first, you can also scan this QR code and this will direct you to a quick survey. And I'll be very, very grateful if you could fill this survey because it will help me prepare better presentations in the future. It is short, it should not take you more than 1 minute to fill. You can also use this link if you don't have your QR code. I will try to copy it. Oh, sorry, wait a second. Try to copy it.
It would be great to have the link.
Yes, yes. Let me try. Oh yeah, I think I can do it like this.
Cool.
Can I copy this link? Okay, I'll do it differently. Okay. And then let me put it in the chat. That should work. Okay, great. So let's see if we have some questions. or maybe we have some comments. Comments are also welcome. Did you find this topic interesting from like your research point of view, or maybe your work point of view? Do you think this is something that could be useful for you?
Alexander, yeah, I found it very interesting. It's not for the time being directly involved, like linked with the project that I'm occupied with, but for my prior projects in neuroscience where causality is a big issue, I liked a lot your conceptual introduction. So that was really good to hear that you think things through apart from coding and doing the software engineering job. So I really enjoyed it. So thank you. Although
Great,
for now,
great.
as I said, it doesn't, it doesn't clip with something specific, but I'm pretty sure it will come because I study graphs and I do drug discovery now. So I'm pretty sure at some point we will occupy ourselves with causality. So yeah.
Very interesting. Drug discovery is a fascinating topic.
I agree. Yeah, it's really nice, and it's relatively speaking quite new as a field. I mean, the intersection with networks and machine learning. So, yeah.
Yeah, great. Thank you so much. Thank you for sharing, and thank you for your very kind words.
Hi, Alexander. I have a question. Maybe just a question to start probably a discussion, more likely than a right or wrong answer. So I was wondering about the discussion between correlation and causality. So we know that machine learning, especially the majority of the models in machine learning, they deal with finding associations between variables. So I was wondering, what is the importance? Of course, it is important to learn causal discovery and to causal inference, but what are the cases that actually causal discovery adds value? Or maybe we can discuss about that, where causality can actually improve the performance. Is this a matter of improving the performance of the model, or actually building a model that better fits the world or the context that we are working on? I don't know, and probably another question is, did any of the models that you describe use a fitness metric that is different from a likelihood or but I guess this is the second question, yeah.
Great questions, thank you. So I will start with the first one. So you asked if causal discovery can bring value in fact, right? That's your first question, and where it can bring value.
Yeah, over the traditional machine learning modeling that deals with correlations.
So there are, I think there are many areas where it can bring value. The most well, the first thing that comes to my mind, but this is probably because of my experience, is marketing. So there's a thing in causality. There's a sub area that is called that is related to modeling something that we call conditional treatment effects. So we're focusing on causal discovery today more than causal inference, but I will start answering your question from causal inference point of view. So you might imagine a situation where you are running a marketing campaign, and now you're measuring the outcomes of your campaign, and you're training some machine learning model to predict when and to what extent you should advertise your, let's say, product. Now, it might be the case, and in reality, it is often the case that among your customers, there are people who are reacting differently to your campaigns. So maybe you have email campaigns. And maybe you have some people that actually read your emails, and then this influences their behavior. So it makes them more likely to buy your products. And this is a dream scenario for you, right? Because you're investing some money, and now from those people, with some probability, of course, or some expected value, you will get some returns. But now there are also people who will open emails, or maybe not even open them. They will just put them in spam. Now, you also might have people that will just buy your products anyway. But maybe even more importantly, you might have people who will stop buying your products if you target them, because they will get annoyed, right? They will say like, hey, I'm buying this, and they are like snagging me, you know? That's annoying. I don't like it. And they will quit. So now with traditional machine learning models, you are usually not able to model this very well because of confounding. So if in your data sets, you will have certain characteristics of those people. And these characteristics from correlational point of view, they might have different proportions than the groups that we just mentioned. So there might be some confounding, right? So there might be some characteristics of those people that will affect both their behavior given your campaign, and also their behavior in general. So usually in these cases, machine learning models are not the most efficient thing that you can do when it comes to modeling. So this is why you're using causal modeling for this. Usually you just use certain methods for causal inference for this. You are not going into discovery, but you could go into discovery if you have enough data and so on under certain, let's say, circumstances that might be useful. So this is one use case. Another use case is in medicine, where when you want to understand what is the impact of a given drug or given therapy on your patients. Now, there's a very nice drawing. I don't know by whom. I think Julia Pearl has it in his book, if I remember. I'm pretty sure I remember this correctly. Can I draw now? I cannot. Maybe I can. I'll try.
Is the example with the cancer patients and drugs, or?
It's slightly different. So yeah, let's do it like this. Okay, this is some data, and here we have exercise, and here we have cholesterol levels. Okay, and maybe somehow surprisingly, we see that the correlation between exercise and cholesterol levels is positive. Well, this is very counterintuitive, right? If we build a machine learning model on this data, this is the effect that we will get. But there might be something else in this data. So there might be age as well. And maybe there are age groups, and these age groups are like this. So now you can see that within each of those age groups, the relationship has the reverse sign. So this means that age is a confounder, because people who are older, they have more cholesterol in general, but they also exercise more. But those who exercise more among the oldest ones have much less cholesterol than those who do not. So now there are certain things regarding proportions even if you control for age in like a regular machine learning model, there might be certain things regarding proportions in your data that will affect the estimates of your machine learning model. And if you don't have this causal information in the model, you are not able to actually remediate this. Does it make sense?
Yes, absolutely, Aleksander. Thank you. Great examples. Thank you.
Thank you.
Yeah.
And your second question, you also had a second question.
Yeah, so yes, I don't want to monopolize the discussion, but I guess it's a small one. The second question is regarding the algorithms that you saw us in the notebook. If you can comment a bit on the fitness metrics that some of these algorithms were in the score-based methods, for example. Just out of curiosity, is this done the likelihood fitness or?
So for instance, most of those methods, well, they differ, but the let's say the classic ones, they are mostly based on things like Bayesian information criterion, BIC.
Okay. I can mention that, yes.
Yeah, this type of stuff. But there are methods like Golem is actually a modification of another method that is called no tiers, which actually is not a very good method for causal discovery, but it contains some very interesting ideas. And these methods actually, some of those methods are actually using machine learning or even like Bayesian generation.
Yeah. All right. Thank you, Aleksander. Great talk.
Thank you. Do we have any more questions?
Aleksander, textual data often contains model descriptions, and extracting model descriptions, are you aware of any work in that domain, combining correlation data with natural language model descriptions to estimate or bias model generation?
Very interesting. Let me just make sure that I got your question right. So what you're asking, about is that you might have a situation where there is a causal relationship that is described in natural language, and your question is if there is any research that could extract the information about the causal model, so build the causal graph based on natural language description. Is that correct?
Yeah, yes, that is one element. The other element is the combination of natural language data with, sample data, statistical data, correlation data from the domain being described. So I'm particularly interested in the combination of the two. Estimating a model, using the data, but in a way that is biased by the causal descriptions in text, or vice versa.
Yeah, so I'm not aware of any research where people would try to actually build a causal graph based on a textual description. There is ongoing research when it comes to causality and NLP. There are a couple of approaches there. People are trying to, excuse me, I need to so people are trying to build a set of assumptions over natural language, and then try to use causal models to estimate causal effects of text. So this is one line of research. So for instance, it might be, maybe you are writing something, you're writing comments on social media. And now we are trying to build a causal model that will explain some type of your decision.
based on your comments in social media, right? So we are trying to understand what is the causal relationship between your natural language sentences or some elements of those sentences and some of your decisions. So this is one line of research. Does this answer a question?
Yeah. So in my domain, one of the interesting problems is trying to extract causal information from text. We have, for example, metabolic pathway charts, which have graphical representations. So we have this convenient form for, and many of these metabolic pathway databases, which are, semantic knowledge bases. Many of them also have attribution information where it describes the source in the literature. So it seems feasible to correlate the, the metabolic pathways with the text which describes them. And this is a case where a causal structure in the real world is being described by text. So one interesting challenge there is to look for other causal descriptions in the literature. See if that mapping can be automated, say the addition of new nodes to the metabolic pathway chart.
I think that's a very interesting use case. What I can do, I can share with you a review article about causality in NLP. I think they do not cover, if I remember correctly, they do not cover anything that would be like literally your use case in structural terms. But maybe you will be able to find some inspiration there, at least some starting points for further research.
That would be great. In fact, in general, if you have any surveys on this or reviews on the subject that are fairly recent or fairly comprehensive that you can recommend, not merely on my use case, but on causal inference in general, I'm sure that many of the participants would appreciate those links.
Great. I have a couple of them. Please feel free to add me on LinkedIn. And I will share this with you. And what I will also do tomorrow, or maybe even I will try to do it today, I will add those papers to the repository that we used today, okay? So I will add a couple of papers. I will just push them into the repository until, let's say, within half an hour from now, okay?
Very much appreciated. I'm sure that many of the participants will make use of that. Thank you.
Great, thank you, Anthony. That's a very very inspiring use case, and thank you for sharing this. Okay, do we have any more comments or questions?
Yeah, so I have also a question. Do you have some kind of a further reading, except of these reviews, but this is more like a, let's say, scientific literature review, but like more like courses or books which are comprehensive about this topic, something like that? Thanks.
Are you interested particularly in causal discovery or in causal inference or both?
Mostly discovery, but I think both also are, is good.
So this is a little bit complicated because I feel that there is no very good material that would be very comprehensive and also practical, I would say. That said, there are a couple of books on this. So one of them is this. I don't know if you can, just let me see if you can see see this, okay. Oh no, you won't see this because it's blurred. So it's Elements of Causal Inference. Let me type it in the chat. by Peters and colleagues. But actually, I would not start with this. If you want to start with something with like a very good review, that would be introduction. Action. Let me check it. I don't remember the title, but I have it somewhere here. It's called Causal Inference in Statistics, a primer. Causal Inference in Statistics, a primer. And this is by Julia Pearl and colleagues. And if you want like an introduction, a great book is A Book of Why by Pearl. And then if you want to go, well, actually I will give you one more. Causality, the mixtape, I think that's the title. It's by Cunningham. Yeah, this is more like econometrics points of view, but it's also very interesting. So I think these 4 books should give you like a good basics. And actually, well, you'll be the first people who hear this in public, but I'm actually working on a book on causality, which will be causal inference and discovery in Python. So it will have a comprehensive theoretical overview, but it will be also very practical and based on Python and written more from a machine learning point of view. Because there's also a good literature in this area coming from econometrics research, but it's a slightly different point of view than a machine learning point of view, I would say. Does it answer your question?
Yeah, it's perfect. I'm waiting for your book then. Thanks.
Thank you. Thank you. Oh, one more book that I thought about is, what's its name? I need to check, I'm sorry. I don't remember the title. But I have it here as well, so it shouldn't take long for me to find it. Yeah, okay. It's called What If. So let me add it here. Most of those books, if not all of them, can either be read online for free, or you can even download a copy for free from the author's webpage. I mean, not from some illegal source. So most of them are available for free in some form, if you want. Great.
I'm sorry, just a clarification. You mean What If book by Randall Monroe from this XKCD comic?
No. It's What If by.
Yeah, I was confused.
It's What If is by Hernan and Robbins.
Okay, thank you.
Yes. So these are the authors in the chat. Okay, great. Do we have any more questions? Maybe the last question or last remark, if anybody feels like. Thank you. Okay, so then I think we are done. Alexandros, did you want to say something?
I would like to thank you so much for this fantastic tour de force. I really enjoyed it. Although I was so busy these days, so I was not so proactive. So I will come back with some questions actually. And have you ever talked to philosophers about causality? It might sound weird, but since you're interested in conceptual things, have you ever had discussions with philosophers of science on causality?
You know, a part of my background is in philosophy of language. So yes, I did.
Great.
I did. Yeah.
Because I have a very cool contact. I really enjoyed to.
Oh, that's great. I'm happy to expand. If you have people in your mind, let's link on LinkedIn and let's talk about it. I'm very happy to discuss this.
Sure. Great. Yeah, so let's wrap it up then and give a round of applause to Aleksander. Reactions.
Reactions.
Thank you.
And see you, in 2 months, guys. Thank you for joining.
Thank you so much for joining.
Thank you so much. So as I said, I will push the papers into the repository within 30 minutes from now. Great. That was a great pleasure to